This is a really fun
Still inside.
Ring the bell loud.
Yeah, I'm getting the hang by day 5 out really.
I don't know how
Okay, so our next talk is going to be by Riad Wahby from Stanford, and he's going to give us a survey of practical proof systems.
Thanks. So before we start, I want to thank the organizers, and also I need to thank Mike Wolfish and Henry Gibbs, who both gave me a little bit of perspective. So compared to Yuval's talk, this one is going to be, let's say, a gear shift. So this is going to be more like a systems-y or implementer's view of the landscape, and the goal is to look at like concrete costs and applications, and maybe at the end I'll present my own sort of wish list. So by now everyone's kind of familiar with the jumping off point, but the idea is we have a verifier that has some computation. I'll use phi for that throughout, and there's some input x and some output y. Maybe it's just a bit 1 or 0. And the prover is going to convince the verifier that the y equals phi of x, maybe with a short proof. And for zero knowledge, we have this additional requirement. The prover has a witness, and the proof doesn't reveal the witness, approximately. So as we saw in Yuval's talk, there's a lot of sort of theoretical work that establishes the basis here. And in the last decade or so, there's been what I think is kind of an astonishing amount of like practical work. Like everything on this slide that's on the columns, it somehow reports on something that they built and tested. So that's just, to me, just like mind-blowing. And in fact, Mike Wolfish gave a talk about 4 years ago right here, and I think that column existed then, maybe a tiny bit at the top here. So like, I think the rate may even be accelerating. So at some point we'll reach the proof singularity. But it's possible, in spite of that I've missed yours, and please, in that case, it's ignorance, not malice. And there's a little bit more room here, so just tell me, and I'll add it. Okay. So we're going to try and get a handle on this, and we already saw this a little bit in Yuval's talk, but we can try and cut apart these things by any number of desiderata and costs. So obviously we can worry about the prover's time generating the proof, the verifier's time, the size of the proof or communication if it's interactive. We could worry about cryptographic assumptions. We could worry about trusted setup, whether the setup is universal or applies only to a single computation. We can worry about interactivity, zero knowledge, the model of computation or expressiveness, and this is actually only a subset of the zoo that we saw before. I'm not mentioning things like public verifiability or this sort of thing. But so I think you've already said this, but I hope that if you take anything away from this talk, it's just that this is some like mega trade-off space. And we're not going to get like one optimal point in the trade-off space. It's more like if you know what your application is, then you can find a point where life is pretty good. But this also means, like this is okay from a researcher's perspective. Henry hates life is good. This is okay from a researcher's perspective because like this means that there's just more to explore, but from an implementer's perspective, like if I have an application and I go and look at this space, there's like some analysis paralysis, right? I was just like frozen in awe of all the sites on the last page. So, but let's try and start to break that paralysis by taking the systems apart. Okay, so we have some computation, phi of x and w, and we can think about a system for making one of these proof protocols as sort of something that converts from our computation phi into two new computations, one that the verifier runs and one that the prover runs. And we can kind of think about that happening in two separate stages, which I'll call the front end and the back end. So in the front end, the computation phi is somehow converted or compiled, and I'm going to use the word compiler more like GCC and less like the way that Yuval did, but a compiler that goes from phi to some intermediate representation, and usually that's an arithmetic circuit, but it's not always. And the goal of the front end is to construct that representation such that its satisfaction is tantamount to correct execution of phi. And then the back end applies some of the machinery that we saw, and somehow turns this into the actual concrete steps that the verifier does and that the prover does. So this is sort of the operating table, and we're going to start to dissect. But I want to give you a couple warnings first. So first, I'm going to try and do. Yes?
So which of these boxes only see phi and not x and w? Just the ones on the left don't see x and w, and the ones on the right do, or?
Let's say, yeah, so this is more like the protocol the pipeline for going from phi without inputs, just the description of phi, to a description of behaviors for the prover and verifier. And then when the verifier and prover actually run those programs, that's where x and w enter. Does that make sense? Okay, so couple quick warnings. I'm going to try and sort of connect the proof machinery to Yuval's talk, but in doing so, it's a little bit of a taxonomy, and I apologize, the slide gets a little dense, but there's smoother sailing after that. And the second thing is, with some of these papers, it's a little difficult sometimes to decide, is this a front end, is this a back end, is it both, is it neither? So if there's something that looks like that maybe should be a front end instead of a back end, or there's one that I lost, maybe I just have a different idea of what constitutes a back end than you do. So sorry about that. Okay, so let's try and connect to the last talk. So we heard about linear PCPs from IK 007 and the instantiation that people tend to use, quadratic arithmetic programs, and the earliest practical systems in this area were based on that. So Pepper and Ginger use the Hadamard PCP, and then basically everything else uses QAP. Let's see, Pepper, Ginger, and Zatar are interactive, as we'll see later, and the rest of these are non-interactive, but we can worry about that in a second. So the other thing I should mention is this ellipsis here hides a lot of refinements to the Pinocchio protocol. So the Pinocchio backend is like a very strongly deployed piece of work, and there have been a lot of refinements to it. So another line of work starts from interactive proofs or multi-prover interactive proofs. So at the bottom, all these systems owe a debt to GKR08, which showed how to make the interactive proofs where the honest prover runs in polynomial time, and also to CMT12, which showed how to go from sort of quadratic or cubic complexity to quasi-linear complexity. And then Thaler 13, Giraffe, and Libra successively refine this till we get sort of linear prover complexity for the problems that these systems can handle. And then on top of that, we have like ZKV SQL and Hierax and Libra and Spartan that show how we can make zero-knowledge proofs out of these things. So I guess I should also mention maybe Blumberg, Thaler, Vu, Wallfish 14 belongs down here, not up here, but I ran out of space. That is based on multi-prover interactive proof. It's called Clover, and Spartan inherits from that and removes the second prover and replaces it with cryptography to get a zero-knowledge proof. So Yuval also talked about MPC in the head, and the practical implementations there are ZKBoo, ZKB++, which refines it, and Ligero, and I know we'll see a talk about Ligero later. And another line of work we can think of as kind of maybe generalizing sigma protocols, it sort of ends with the bulletproofs line, ends for now, with the bulletproofs line, and this one gives like very short, like concretely short log-sized proofs. And then there's Aurora and Stark, which build on IOPs and also on the arguments and CS proofs of Killian and Macaulay. And last but not least, we have the polynomial delegation-based schemes like Sonic, and I think we hear about Sonic this afternoon. But this is sort of based on the polynomial commitments of Kate Zavarucha and Goldberg 10, and then some later refinements to that. So this is too neat in some sense, because it seems like everything just inherits from one line of research, and that's totally not true. There's all kinds of cross-linking here. So let me give you a few examples. So Sonic uses the same arithmetization as bulletproofs, which comes from the work of Boodle et al. And the line of work that includes ZKV SQL, VRAM, and Libra uses polynomial delegation, or sort of a follow-on to that by Papamantoshi and Tomasia, that is verifiable polynomial delegation and some zero-knowledge variants of that. And another example I think we'll hear from Mutu on this, Ligero, you can think of as sort of an interactive PCP, which is sort of in the line of IOPs. Maybe we can think of it as a restriction on IOPs. So this is an oversimplification, but kind of gives us pointers to where the intellectual debts are. So we can also start slicing by setup and cryptographic assumptions. So when I say trusted setup here, I mean a specific thing. I mean we have a computation that outputs what we call a structured reference string, and the reference string is used during proving and verification, and the important thing to know is that if the structured reference string is generated dishonestly, then you can prove false statements. So you can see why we maybe don't want to have a structured reference string, and in fact there's been a lot of work on getting rid of structured reference strings recently. But some systems do use a trusted setup, and some of them use what's called a universal trusted setup, and the idea here is that once we've done the setup once, then at least up to some size bound, we can execute any computation that we want using that same trusted setup. And within this category, we can divide a little more finely. Sonic has this very cool property, as I guess we'll see in the next talk, that the trusted setup is actually updatable, which means if somebody's already done the setup, then I can take it and run a computation on it and get out a new setup, and then I should trust that that one is okay. And then you can also believe that I actually correctly translated the old trusted setup to the new one. So maybe we can all be happy. And we can think about this as maybe a slow motion multi-party computation, right? I do it and then like tomorrow somebody else does it, and eventually everyone has contributed their own randomness to the reference string. And then finally, most of the early practical systems in the area rely on a trusted setup procedure that is per computation. So if you want to run a different computation, then you have to run a new trusted setup. So within even these categories, we can break things down a little further. So let's ask, what are the assumptions? The interactive proof and multi-prover interactive proof-based schemes have unconditional guarantees, not zero knowledge, and of course, they require interaction. This group here, ZKBoo, ZKB++, Ligero, Aurora, and Stark, are based on collision-resistant hash functions, and they can be made non-interactive in the random oracle model, and they're plausibly post-quantum secure. Let's see, bulletproofs, Hyrax, Spartan, and also Pepper, Ginger, Zatar are built on some Diffie-Hellmanish assumption. Although I guess I should say Pepper, Ginger, and Zatar are private coin and non-zero knowledge, and bulletproofs, Hyrax, and Spartan are public coin and can be made and zero knowledge, so they can be made non-interactive. And then we have the systems based on the Pinocchio protocol, and also the ones that use polynomial delegation, and those are some sort of knowledge of exponent or related assumption. Nowadays, I think most everyone who's using Pinocchio-style protocols is actually using the Jens-Groth 16 argument, which is in the generic group model. So that's stronger than knowledge of exponent in the sense that in the generic group model, you can prove a knowledge of exponent type statement. And then I should say Sonic is not actually, it's a little stronger than the standard model, but a little weaker than the generic group model is in the algebraic group model. Okay, so, okay. We're gonna keep going, So we're gonna slice one more time. We could ask a couple different questions actually, but these are quicker, I promise. So we could ask like, how does the per computation trusted setup amortize? Because this is also sort of interesting, right? And it turns out that the Pinocchio-based protocols, once you've run the trusted setup for a computation, then you just get to keep using that setup forever. Whereas in the earlier work, the Pepper, Ginger, Zatar work, you have to run the trusted setup, and then you can use it for a batch of computations, but once you're done with the batch, you gotta rerun the trusted setup. One more, okay, just one last one. Okay, so then within universal trusted setup, we could ask, what is the cost of universality? And it turns out that, so some of these systems, we're gonna see this later in more detail, some of these systems get universality basically by emulating a universal circuit on top of arithmetic circuits. And so that emulation has some cost built into it. On the other hand, so that's like the libsnark with VNTinyRAM and VRAM have this flavor. And then something like Libra or Sonic, the universality is sort of at a lower level. It's more inherent to the protocol. And so there isn't this layer of abstraction where we have to pay first for a universal circuit. Okay, we're done with that. All right, so now that we've gone through some of the desiderata, yes. Oh, okay. Now that we've gone through, now that we've gone through some of the desiderata, let's look at concrete performance type numbers. So it's important to be clear that one graph is not the answer to your performance questions. Like this is one application, and this application tells us how these things perform on this one application, but we're trying to get some like sort of equal footing idea of how things work, and this is an approximation of the truth. So the benchmark here is proof of knowledge of the leaves of a Merkle tree. So the public input is the root of the tree, and the witness is the purported leaves, and then the checking computation just recomputes the root using SHA-256 in this case, and then checks for equality. So the x-axis is the height of the tree, and the y-axis here is proof size in kilobytes. So, you know, kind of going from the bottom to the top, libsnark, which is the only one on this slide that uses trusted setup, libsnark, super small, bulletproofs, things start to grow a little bit, Libra, Hyrax, what is this, Aurora, Licero, and Stark, and then finally at the top, ZKB++, which goes, you know, I mean, most of these are sort of hundreds of kilobytes at most, maybe 500 kilobytes, and then this one goes from, you know, a megabyte to hundreds of megabytes. So this is sort of the range of proof sizes. And maybe one thing other than just like reading data off the slide to you that I can point out is, look, we all know that asymptotics aren't the whole story, but there are a couple specific examples here that I think put that in sharp relief. So one is bulletproofs is logarithmic in the circuit size, and Stark is log squared, but there's sort of 2 orders of magnitude difference, and the log factor doesn't explain that. What does explain it is bulletproofs actually has like super small concrete multiplier in front of the big O hides like 50 bytes or something. So it's very nice and succinct. And the other one is Hyrax, in this case, goes as cube root of the circuit size asymptotically, but concretely it looks nothing like cube root. And the reason is that one of the low order terms in the asymptotics is actually what's dominating at these sizes. So it looks almost flat. Okay, so that's proof size. How about prover time? So this is prover time single-threaded, which we can think of as sort of the total amount of work that it takes to generate a proof. And I should say that some of these systems can run in multi-threaded mode. For example, the Stark implementation can handle dozens or hundreds of threads. And that's like a sweet, like when you actually want to generate a proof, but it makes it hard to compare things. So here we're just looking at single-threaded. So remember on the last slide, ZKBoo had really big proofs, and bulletproofs had really small proofs, but here we see that the fortunes are sort of reversed. ZKB is like super quick, and bulletproofs is you know, it's a little slower, a little more challenging. And then between the extremes, we kind of have, maybe we can think of it as 2 strata. The more expensive ones are Hyrax and Aurora, and then the less expensive ones are, I guess this is what Licero, Libra, and libsnark, kind of a little better than the median. So I should note a couple things here. First, libsnark in this case is not the universal version. This is the one that uses a per computation trusted setup. We're going to see concretely what the cost is of the universal version later, but here we're just looking at per computation trusted setup. And the other thing that we should be asking is, what is actually the cost of that trusted setup? And the answer is, roughly speaking, you can think about the cost of the trusted setup in libsnark as about 2x the cost of running a single proof. So it looks very similar. Okay, and then the last thing I haven't told you about is the verifier performance. So libsnark has short proofs and extremely fast verification, and the reason for that is that there's this trusted, you know, pre-processing step. So a lot of the work is happening in the pre-processing step. In contrast, if we look at something like bulletproofs, there's no pre-processing at all, and so the verifier, as part of verification, actually has to read the whole computation that it's verifying, and so this ends up meaning that there's some linear cost, and actually that cost involves public key crypto. So this explains sort of the concrete costs. But now we should be stopping and thinking for a second, because I said a couple slides ago that everyone except libsnark is free of trusted setup, and yet there are plenty of verifiers on this slide that are sublinear somehow. So what's going on? What's going on is the sublinear verifiers that don't require trusted setup are taking advantage of some structure in the circuit. So as a couple examples, Stark has a model which requires essentially expressing the computation as the repeated application of a state machine transformation. So the reason that the verifier can think about that very quickly is because the description of the state machine transformation is very small. Or in the case of, say, Libra or Hyrax or Ligero, they can take advantage of the fact that the verification circuit is actually, in this case, many evaluations of SHA-256. So there's a common structure there, and all of them can extract that common structure. And then let's see. So Aurora, Bulletproofs, and ZKB++ are sort of in the boat where they're not taking advantage of structure. Although certainly in the case of Bulletproofs and possibly in the case of the others, there is some possibility for taking advantage of structure, say batching the proof of the same computation many times. And I don't picture Sonic here, but in that case, I think we'll see this in the next talk, there's this possibility to take advantage of an untrusted helper who batches together proofs for many different statements. And there we end up with a similar thing where incrementally the cost is sublinear is constant for each proof. Okay, so we have some notion of how these things perform concretely. So let's go back and take a look at the front end now. So remember, the front end is going to convert our computation phi into some representation. And so we can kind of slice the front ends in two different ways. We can either think about the machinery that it uses to actually compile from a high-level language into a representation, or we can think about the representation that it's actually targeting, right? And so we'll start there. Let's think about the representation. So I've alluded, I think a couple slides ago, to like two different approaches here. The first one is roughly to translate the computation into an unrolled finite state machine. So essentially running the program on a CPU where the computation is the fetch, decode, execute loop of the CPU. And so this is the approach that BCGTV13, BCTV14A, BCTV14B, CTV15, they take this approach. And they introduce the tiny RAM architecture. And the idea there is really beautiful because it kind of sidesteps the problem that in the Pinocchio-style protocols, you have to run a per computation setup. So here, the computation is just the CPU, and then we can compile our program using any compiler. I think actually BCTV14A actually modified GCC, so they could just run their program through GCC, and then they run the program as software on the emulated CPU, which is super cool. So the only downside to this is that there is some cost associated with it. Again, we'll see it in a little bit. VRAM, that's this one, ZGKPP18, takes a similar approach, but they take advantage of the fact that the setup in their scenario is not per computation, which means that they can actually optimize the CPU on the fly for the program. So that's kind of super cool. And actually, Starks take a similar approach, but for different reasons. I mentioned in Stark, we want to be able to apply the same transition function many times. So there, we have to sort of get a concise description of the transition function. And so we end up with something very much like a fetch, decode, execute loop, or in some cases explicitly a fetch, decode, execute loop. Okay, so if that's a CPU, then we can think of basically every other work as being an FPGA. So the idea is we're going to translate the program line by line into a circuit. So actually there are a few systems where it's worth noting the shape of the circuit also matters, not just the contents. So the GKR-derived circuits want a wide and shallow circuit because depth figures into the costs. And so in all of the circuit-ish and all of the FPGA-ish cases, there's sort of something like unrolling the execution of the CPU. Here it is that the computation time turns into space in the circuit. And it's actually even worse than that because things like conditionals actually turn into space where all the conditionals get executed, and then we select the one that we wanted. But actually, it gets even slightly worse than that. Because, so I'm saying here I0 greater than or equal to 5. Remember, this is basically turning into an arithmetic circuit, and there's no really concise way of expressing I0 greater than or equal to 5 in an arithmetic circuit. So what do we do? Well, okay, so what we do is we ask the prover to convince us that I0 is greater than or equal to 5 by giving us a bitwise expansion of the difference. So we're going to call I4 I0 minus 5. So give me, please, I say to the prover, the bitwise expansion of this value. And then first I have to check that it's actually the correct bitwise expansion. So I compute, I compare the two. And then I have to check that all the bits are actually bits. They're either 1 or 0. Which I do by checking that either 1 times 1 minus is 0, okay? And then finally, I check effectively the most significant bit of the bitwise expansion, and sort of in 2's complement fashion. If that's 0, then I know it's positive, and that means that I0 is greater than or equal to 5. So this blows up a lot, right? If I have a k-bit number, then I need something like k plus 3 constraints. And this is true for comparisons, for arbitrary modular reductions. There are a lot of these things that we think of as kind of natural computations on a CPU that are actually very unnatural in this model. And I want to be clear that I'm picking a little bit on the FPGA people here, but the tiny RAM and the CPU style computations also pay this cost. It's just sort of in the CPU state transition function. So in there, there's bitwise expansions for things like the AND function or the XOR. So this is sort of the representations. Another thing, as I said, that we can look at is how the compilers themselves work. And this is the last one of these taxonomies. But here, this is sort of, there's a trade-off space between expressiveness and cost. And so we can, roughly, you can see this as sort of a frontier where up and to the right is a little better. So the very lowest costs come from systems that do some sort of special purpose computation. So Thaler 13 is a good example. There's a super fast matrix multiplication proof protocol there. It's special purpose. It's also super high performance. Another example is vSQL, which sort of observes that, look, SQL queries are essentially data parallel operations, so they use the data parallel protocol from Thaler 13 to execute, and plus a bunch of other very cool optimizations, to execute the SQL queries in parallel on all the rows of the database. And then we have these sort of gadget libraries, Bellman, Gadget Lib, Lego, Snark, Coco, and probably some others that I'm missing. And the idea there is somebody can develop like a very efficient, for example, a crypto primitive, and then I can, I don't know how to do that, but I can just sort of wire together these very efficient primitives. So there, the goal is to sort of attack the really hard problems and then let me wire them together. So if we move to the right, then we get these systems that essentially can compile pure computation. So no I/O, just arithmetic, this sort of thing. So Pepper, Ginger, Circom, Pinocchio, Zatar have that flavor. And then as we move up a little bit, Allspice does a little more than that. So it does that, but then it also does some program analysis and says, oh, maybe this proof system would be better for this computation, or maybe this proof system would be better for a different computation. And Giraffe kind of goes in that direction too. It tries to slice apart programs and say maybe this piece is good for outsourcing and this other piece is bad for outsourcing, and the verifier should execute that locally. So clearly that's not for zero knowledge, but you can see how in the outsourcing case we only bother to outsource the things where the prover can actually help us. As we move to the right again, now we start to get into stateful computations. So Pantry, AdSnark, Geppetto, and XJSnark in approximately increasing order of speed can work with memory, with I/O, and there essentially the way that it works is there's sort of commitments coming in and then computations over the commitments and a new commitment going out. So we can sort of have verified operations on state. And then finally, all the way to the right is the systems that work essentially in the CPU-ish or the state machine transition model. And we've seen most of these before, except I haven't mentioned Buffet yet, and if I'd been better with tech, I would have moved Buffet over a little bit because it's not quite as expressive as the others. So in Buffet, the idea is we can use program analysis to turn complex control flow into a custom state machine that only applies to that one program, but it means that we don't have to pay the overhead of the CPU. We just pay the costs of the one program. And so what this means is there's no notion of program text in Buffet, right? So there's no program memory, which means I can't do things like function pointers or self-modifying code. So it is restricted compared to these other systems. But as we'll see, like in 2 slides, there's a little bit of a trade-off here. Well, here we are. So this is a comparison of just the front end. So the back end here is fixed. The back end is libsnark, which is we saw a little while ago. And so we're looking at the 3 approaches here. I'm sorry about the rendering there. It looks a little bad. Pantry is it represents the sort of FPGA approach. BCTV14A is VN Tiny RAM approach. And then Buffet is sort of the hybrid between the two. Before we look at this, XJSnark, I don't have data for it because it doesn't quite handle the sort of state machine transformation computations, but it does improve on Buffet's memory handling and things like this by about 3x. And also, I should mention VRAM. It's a different backend, so it's difficult to put it on one slide and kind of make sense of it. but it uses the CPU abstraction, but because of some very nice optimizations that I mentioned, and also because it's using a proof system that's a little easier for the prover, it ends up sort of recovering a lot of the cost of the CPU abstraction. So you can think about VRAM as approximately as fast as Buffet, except actually on matrix multiplication where it can use Justin's super fast matrix multiplication protocol. Okay, so those aside, what we see is, so matrix multiplication is a great example of a computation where it just turns straight into an arithmetic circuit, right? And so there, the CPU abstraction does basically nothing for us, and it costs us a lot. But as we start to get into these computations that need to work with state or that have complicated control flow, then the CPU abstraction starts to really help us compared to trying to turn this complex control flow into a flat circuit. But with Buffet, we can avoid paying some of the costs of the CPU while still having that approach where we can comprehend complex control flow with essentially a state machine.
Go ahead.
You mentioned before that one of these systems, I don't remember which, sort of analyzes whether the computation is more, I guess, algebraic or more. So this kind of thing would be done there? Like they would know where
these three don't do that. The one that does that is, I think I mentioned Allspice. Yeah, so in that case, basically, you could imagine adding a similar program analysis to any of these. But the idea there is basically just sort of try and compile the circuit and then apply some model of the cost, say, for, I believe it uses GKR/CMT as one of its options and, Pinocchio style, like libsnark for the other option.
they don't look at the type of computation, the I/O or something, or to determine which.
Yeah, I think you could probably do it either way, but in fact the way that it's done there is first we compile and then we see, like, is this thing low depth enough that the costs would be worthwhile in GKR versus in libsnark or Pinocchio. Does that make sense?
Yeah.
I think there was another one.
Yeah, so just to understand the numbers here are what is it's running time of the libsnark prover? And
Yeah, sorry. Thank you for the question. So everything here is running time normalized to Buffet on this slide. So this is just the prover.
You're giving it to the libsnark prover in the end.
Exactly, yeah. So this is only proving.
What, a C program and ending with the libsnark prover and all of the three?
Yeah, actually, I think in the BCTV case, we didn't have a compiler that targeted TinyRAM, so we actually wrote the assembly by hand. But it starts from some high-ish level description of the computation. So yeah, in all of these cases, we have a computation that's like merge sort written in C or maybe hand translated into assembly. But it really is something that you can run on a normal computer, and then we turn that into a computation that you'd run in one of these proof systems. Does that make sense?
Compared to Checkable, for example, when compiling a...
Great question. So I think Geppetto handles certain kinds of computations better. Yeah, so this as you're pointing out, this is very incomplete. So Geppetto handles computations where there's sort of state passing between sort of large sections of a program. So it handles that sort of thing much better. I think it doesn't have it doesn't implement the sort of state machine to circuit, or rather program to state machine transformation, which is really in some sense what we're looking at here. But if it did, then yeah, it would get sort of the same performance as Buffet, and then it would additionally get this ability to sort of very efficiently pass data between chunks of a computation. Does that make sense?
Yeah.
Okay, so we've looked at this, we've gotten comfortable with it, but it's sweeping something pretty unfortunate under the rug. Namely, we're kind of looking at like 2 orders of magnitude at best or maybe a few orders of magnitude at best in terms of optimizations. But if we put native on the scale, then like suddenly life doesn't look as good. We're like 6 orders of magnitude behind where we want to be. And I want to be clear, I'm not picking on these systems and I'm not picking on the libsnark backend here, because remember we looked at this earlier and libsnark is actually faster than the median. So like in all of these cases, we would have this huge blow up. Maybe it would be 4 orders of magnitude instead of 6, but like somehow this is kind of a nightmare. Well, maybe it's not a nightmare. Instead, maybe we should think about this as what I had a manager who used to use the phrase opportunity to excel. So I think that this is an opportunity to excel. So Okay, so the other reason that maybe we shouldn't be too depressed is because there really are cases where we're willing to pay a lot of prover time. Like, I can go to Amazon and rent 100 servers, so like, it's okay if a computation is big, because there are a lot of processors in the world today, and like somebody else owns them, which is great. But maybe there is a different sense in which we should be depressed, and that is if we look at the reachable computation size, this isn't just like how long it would take, this is like, can we do it, period. So to look at that, instead of looking at like how long each one takes on a fixed program size, let's look at how much work we can get done, or sorry, how long each one takes on, the same program. Let's look at how much work we can get done for a fixed circuit size, right? And so here I'm fixing it at 10 million gates, which is about what you need on, a reasonable computer that has like 16 or 32 gigs of RAM. And so if we do that, then what we see is that we can support up to, I don't know, like a 500 element merge sort, which is like, I mean, you fire up Python and do that, like you don't even think about it. Or like a 200 by 200 matrix multiplication, like we do that in MATLAB and don't, again, it's like a millisecond, whereas the prover takes 20 minutes to generate the proof. So like we should be a little worried that we maybe can't reach program sizes that we really would care about. But I should say that VRAM pushes that up by another order of magnitude. So things are getting better. We're getting bigger. But we could ask, like, what else could we do? And maybe there's some intuition in what I just said. Like, I can rent 100 servers from Amazon. So why don't we try doing that? And that's exactly the question that Wu et al. Asked with the DISC, or distributed zero knowledge work. And the answer is, well, let's just throw more computers at it. And so we're going to run the prover as a distributed computation now, instead of on a single machine. And that is way easier said than done. So DISC targets the Pinocchio-ish libsnark kind of backend. And there, inside of the QAP, there's this giant FFT that we need to compute. And unfortunately, it turns out that like distributing the FFT is like a totally non-trivial problem. But fortunately, there was some work by Tse in 2011 in the context of multiplying like terabit integers in a MapReduce cluster. So this is a distributed computation where we end up with 2 batches, each of size square root n, where each piece of work in the batch works over a computation of size square root n. So there's a concrete blow up there, and there's actually a lot of communication between the 2 batches. But the nice thing is that while these tasks are executing, it's all local computation that's only about square root n size. So this is like a huge advantage for us for one of these proofs. So DISC takes this approach, and the results that they show are super cool. So they show 100x larger reachable instances compared to this former state of the art. And so in particular, on their cluster, they could get sort of 1 million-ish constraints with one computer, and a couple billion with a couple hundred computers. But that's like easy to rent from Amazon. Like I go there and I click a button, and like 100 computers just materialize. So this might seem like a lot, but actually no. This is like your web browser can do this to first order. And it costs like $20 an hour or something, so it's like great. And the other question we could ask is like, how fast is it? And this is showing us sort of speed versus the number of workers. And if we draw vertical lines, that kind of tells us how it's scaling. So if, for example, if we just look at like how long it takes 4 workers to do something and how long it takes 64 workers to do something, we really are going from like hours to minutes to run these things, which is cool. So this means maybe there's hope, even just with sort of systems-y work, to scale these things up to computations that are big enough to really get done what we care about doing. And so having said that, let's take a look at some computations, some applications that maybe we care about.
Do you have to trust all those computers and Amazon to not produce them?
Yeah, so in the case of DISC, this is a great point. The prover there, it really is all 200 machines, and so each machine gets to see at least a little piece of the witness. So there's no statement of, the witness is hidden or something like this. So yeah, this is a question that we could hope to answer is, can we get this without trusting the cluster? Yeah, I agree with you. And thank you, it's a great point. I'm sorry? Yeah, exactly. Okay, so let's take a look at some applications. So we weren't going to get out of this without talking about cryptocurrencies, but the reason for that is that there's a lot of a lot of cool applications in the cryptocurrency space. An obvious one that I think we all probably know about is Zcash. So it's based on a paper from 2014, Zero Cash, I think was in the title. And it uses essentially proofs as transactions. And roughly speaking, what that means is that your transaction doesn't reveal who you are and it doesn't reveal how much you've spent, which is cool. And in fact, there are efforts to incorporate this same kind of idea into other blockchains. So Greg Maxwell, I think, proposed confidential transactions, and they're building them on top of bullet proofs. Another application that I think is super exciting is Coda, which is a project from Order 1 Labs. And the idea there is to use recursive proof composition so that if you want to verify the whole blockchain, all you do is download like 20 kilobytes and then verify one proof, and you've got the whole history verified in one go. So that's already cool, but I think the thing that maybe the lesson that we can draw from that is that like there are now applications where we can start to hope using like recursive proof composition in a practical way, and we should be excited about this because this is like a new tool, a new weapon that we should be deploying to get some of these applications. And then I can't resist mentioning one more. It is illustrative. I've some work with Dan Bonnet and Chris Jeffries and Joseph Poon on what are called private airdrops. So here the idea is I'm going to give you money, but you don't want to reveal that you took the money. So instead there's some like privacy aspect there. And I'm not going to go into details except to point out that this is not a general purpose proof system. And we actually looked at how much it would cost if we just wanted to implement this in sort of the straightforward way with any of the general purpose zero knowledge proof systems that we could hope to use. And the answer was it was very, very expensive. So I think the lesson to take away from this is within this design space, there are also these specialized proof systems that we should go to first if we can. If your statement is simple, try very hard to use something specialized because you'll save orders of magnitude, it turns out, at least in this case. Okay, but I want to go into a little more detail about one other cryptocurrency application, and it's called Rollup. And from what I know, it was suggested by somebody called Barry Whitehat. So the setting is, I want to build a bank out of a smart contract. And so the way this is going to work is when Alice wants to send Bob money, she signs a transaction and sends it to the bank. And then, maybe Bob and Carol do the same thing. And the picture that I'm painting here is bad for a couple reasons. So one, the smart contract has to verify all of those signatures. And doing that means that the smart contract has to burn money, and it also has to pay for the data transfer. And on top of that, it's going to be extremely slow. So as written, this doesn't work. But here comes the roll-up idea. So the idea is, what if we add in a third party? This is an untrusted third party called an aggregator. And so now when Alice, Bob, and Carol want to transact, what they do is they send their signature to the aggregator. And then periodically, the aggregator is going to create a batch of these transactions and summarize them in one proof and send that proof to the smart contract. And then all the smart contract has to do is check that one proof. So obviously, we're relying on the aggregator here for liveness and also for privacy, and those are additional opportunities to excel. But we can think about, like, this is kind of an interesting, verifiable outsourcing looking application where we're additionally using the zero knowledge property almost to get data compression. So you can also alternatively think about this as, one level of proof recursion. The signatures are a proof, and then there's a proof about the proofs. But the idea here is very nice, and it turns out it's quite practical. Okay, so that's one application. Totally separate application, not in the blockchain space now, is an idea from Seti, Angel, Gupta, and Lee at OSDI 18, and this is called Spice. So the idea here is I want to build something like Stripe or WePay or something like this, where I can send money to people sort of by connecting to the central server, and then the central server has like some database or some backing store, and it's storing all the transactions in the backing store. But what I want to do is I want this to be auditable. So every once in a while, the service should send out some proof that it's been working correctly. And in principle, we could have done this based on existing things. Well, not we. They could have done this based on existing things like Pantry or vSQL, which both support these verified storage primitives. But the problem here is specifically with getting concurrency, because we want to be able to have, so for example, if we used Pantry, then you have a commitment to the current state of the world, and then a proof transitions us to the next state of the world, and there's no way to do that multiple times in parallel. So we want to be able to do this concurrently. So to get this, the authors draw on some work in the memory checking literature, and they design what they call a batch verifiable set-based key value store. Lots of hyphens. So the idea in the top left of this diagram is we start with some state of the world that is expressed as two sets, a read set and a write set. And any time that somebody reads or writes to the store, that updates the sets. And then later we can check that all of the reads were correctly serviced from previous writes just by checking that the read set is a subset of the write set. Okay, and I'm not going to prove that to you, but that's the idea. And so this is like somehow it doesn't catch, for example, which read was done incorrectly. It only asserts yes, all the reads were done incorrectly, or no, there was at least one error. But in this service model, maybe that's good enough. And then on top of that, we can use a zero knowledge proof to make this statement into a compact and obviously zero knowledge thing. And then that is actually what we send to the auditor. So now we can tell the auditor sort of every 10 minutes or something, yes, everything was fine in the last 10 minutes. And so the results, performance-wise, are like 4 orders of magnitude better than what could be done previously. So to me, this is a nice lesson in like taking advantages of the strengths of the tools and the weaknesses, or at least avoiding the weaknesses. So here, the zero knowledge proof scheme is being used to implement business logic, which it's great at. And then on top of that, there's this additional piece of like a concurrency primitive that's enough to get the application to work. So maybe we can think about this as sort of a point between full generality and application specificity, where we take what we need from each one. Okay, one final application, and I'll go through this one quickly. What if we want to build trusted hardware? And so this is a question that we started from, some co-authors and I started from. I'll have their names up, I apologize, it's not on this slide, a few years ago. And so the question is like, okay, I want to build a chip for a firewall. And I want to make sure that even though I don't own the company that's actually building the chip, like I design it, but then I send it off to TSMC or somebody, and maybe they're going to insert some backdoor into the chip. And for example, maybe the backdoor will listen for some secret sequence of packets and then let an attacker take over my phone. And this maybe seems like paranoia, except I think this article is from 2012, and the claim was that already we should be worried about counterfeit or possibly malicious devices. And so the US government, for example, is very worried about this, and they have a special program that is there to try and detect and prevent attacks of this sort. And to do that, they make sure that all the contractors have background checks, and they have like chains of custody and couriers for the designs that are going from the design house to the fab. And the reason for all of this sort of activity is that there's been a lot of work in the last few years on attacking chips, like inserting backdoors into chips. And the high-level message is that that you can do this essentially with impunity. If you're the one building the chip, you can put a backdoor in it and no one will ever know. So this idea of having a trusted fab, though, isn't so great. Because, well, there are only a few places in the world where you can actually build really fast processors. And if we want to start doing that here, like we're going to spend $10 billion, and then maybe in 5 years we'll be able to make some processors. Or maybe the fab won't work and we'll have to spend another year like Intel's been. So the alternative is I can just go and buy an old fab. It's cheap. No one really wants it anymore. But then the physics of semiconductor scaling starts to kill me because now I pay like 8 orders of magnitude in performance. So the idea in this application that we call verifiable ASICs is we're just going to apply the outsourcing regime to chips. So specifically, remember we have our computation phi, and what we're going to do is we're going to actually turn it into 2 chips. One called the prover and one called the verifier. And the prover we're going to build at TSMC or whoever makes the fastest chips today. And the verifier we're going to build at our own private trusted fab. And then we'll put them together, and then this is the device that we actually run. So when I want to run a computation, the verifier talks to the prover, and I get out an answer that I believe is correct. And so So the question, like the high level question is like, does this work? I mean, I'm claiming it's an application, so what does it look like? So this is some simulations, we haven't built any chips yet, of elliptic curve point multiplication. And here, the prover is in like today's technology, like 7 nanometer, and the verifier is in like 20 or 25-year-old technology, like quarter micron. And so what we're looking at is energy cost. So on the y-axis is the energy that it takes to run the batch of computations, and on the x-axis is sort of the number of computations we run in parallel. And the baseline, these blue dots, is just running the computation on the trusted chip. So what we see is that sort of after 30 parallel computations or so, we actually can beat the native baseline. So this is an instance where we can do like verifiable outsourcing and actually get some benefit. And maybe we view that as a positive result, and rollup is another example of a positive result. But actually, when we started working on this, we kind of set out to answer this question, like, does it ever make sense to outsource? And this is an instance of where it does, but it's almost depressing that you have to go this far to find something where it works, right? Like, this is a very specialized case. Benedict, yeah?
Shouldn't the verifier be able to take advantage of set linear verification cost at some point? Why does the verifier scale linear?
Yeah, so here, this is in a proof system where the verification cost eventually, like asymptotically, ends up tracking because we have to sort of check the sizes of we have to work over batches that are inputs that are basically order the size of the circuit. So in this specific computation, there's no sublinearity. So the underlying system is GKR and eventually Thaler 13 here. And the size of the inputs is proportional to the size of the circuit. So this is why the verifier eventually looks asymptotically just like the size of the circuit. You might hope to take advantage of like sort of, I don't know, commitments or something like this that would make that better. But here we don't.
Why would you think that this is an off that, like on the corner, this is more important than the other ones probably?
Yeah, I mean, I believe it. I agree with you. I think that we should be doing things like this, and I'm hoping that we actually start building chips like this. But on the other hand, like the original dream was, a laptop controlling a herd of supercomputers, and we haven't quite reached that dream yet. So in that sense, we're still searching for the pieces that are going to get us to, real practical outsourcing. Okay, so that's the end of the applications. And now I promised a little bit of a wish list, so here I'm going to tell you everything I want for Christmas. So it's it's back-end wishes and then front-end wishes, and some of them are theory-ish and some of them are systemsy. So I hope everyone gets a wish that they can work on. So in the back end, the first wish is that we can start to avoid using FFTs. They're currently a major bottleneck in QAP-based and IOP-based systems, and to be clear, my goal is not to impugn the FFT because it's somehow the crown jewel of 20th century math or 19th century math, depending on who you ask. But it's just, I want to observe that like FFTs, like if we're doing an FFT over something the size of the circuit, then we're never going to get past the quasi-linear barrier, right? We're always going to be at n log n. So asymptotically, we should worry about this. And also concretely, we should worry about this because it's memory and it's communication intensive. And look, DISC distributes it successfully. But like the amount of work that it took, maybe we could hope to avoid in the future. So that's wish number one.
Breaking computation into subcomputations, applying FFT to each subcomputation, and then recursion.
Yeah, absolutely. So it may be that really the answer is not avoiding it, but only applying it to very small pieces of the computation. Absolutely, absolutely. Second wish, and this echoes something that you've all said, is I wish for super succinct, super efficient, multilinear polynomial commitments without trusted setup. That's a lot. So right now, any of the zero-knowledge systems that are based on the interactive proofs or multi-prover interactive proofs are kind of bottlenecked by their polynomial commitment scheme. So for example, in Hyrax, the verifier kind of pays a square root cost in the size of the witness for the commitment scheme, or if we want to shrink the proof, then the verifier's work goes up to linear. In vSQL and VRAM and Libra, the performance is great, but instead we pay for a trusted setup. So it would be nice if we could get the best of both worlds. And I think if we had that, as you've all pointed out, we would immediately get super efficient zero-knowledge proof schemes. A third wish is I think another one that you've all pointed out is MPC in the head beyond the square root barrier. So I think one of the key takeaways I thought from the prover performance slides was ZKB++ and Ligero are both super fast. And on top of that, they have very, very minimal complexity or cryptographic assumptions. So this is the main thing that we should start to worry about is like, well, the proofs are a little big. So I hope maybe for a positive answer to the question, can we break the square root barrier and still keep the super speed and the nice assumptions? And then the final wish for the back end is for systems that have updatable structured reference strings like Sonic to also have updatable proofs. So let me explain what I mean. So remember in Sonic, I have a reference string and you don't trust it, so you update the reference string and now you trust that one. But if I generated a proof with my reference string, then you need to keep my reference string around in order to check that proof. It would be really nice if we could have sort of an untrusted process by which proofs over old reference strings get updated into proofs over the new reference string. And you could see how immediately that would make this sort of model extremely, extremely powerful. There is some work on this. I was just going to point out that Helger Lippmann has some work on this for a restricted class of computations. And so the question is really like, how general can we get? But probably, if we think about it carefully, we can't hope to get too general or too efficient at this, because otherwise it would be equivalent to getting rid of the trusted setup entirely, I think. Yeah, Ali?
Add one. We have very, very few practical post-quantum solutions, and I think that's another problem that spans both.
Any?
Sorry?
Any?
We have very few.
No, I'm asking any?
It depends how much you care about proof size. I mean, things in a random Oracle model, they are post-quantum.
So nothing specifically was targeted for that?
Yeah, we have some lattice constructions, but they're not as, it's definitely probably not practical so far. I think it's another big wish. And it is my mind.
In the designated verifier case, it's much better, right? In the designated verifier case, it's much better.
Right, so we know things for designated verifier.
And for example, the work on post-quantum signatures would benefit from this too, potentially. So this is something that would be extremely beneficial.
But if you go to quantum, so what do you mean by sequence? You have to define things. What a simulator does. Is it classical? Is it quantum? Classical with quantum order to quantum adversary. You have to define NISIC. Quantum zero knowledge is not something which is.
I think in a very simple empirical. I mean, I think from the kind of perspective, like post-quantum means something that cannot talk, that we don't know is broken for sure.
Yeah. So maybe item 5A is a good model, and item 5B is a construction for that model, right? I mean, or opportunities. Okay. So back end. How about the front end? So the first wish is moving beyond the arithmetic circuit model of computation. So we've already seen that some works do, TinyRAM, VRAM, Stark, they point the way for us. But there are a lot of computations that we consider natural, SHA-256, XOR, that are ugly when we turn them into arithmetic circuits. So actually, in this very spot 4 years ago, Mike had exactly the same wish, and his suggestion at the time was that we should start making friends with the programming languages folks, and he was right. We should have been making friends back then, and we should also now start making friends with the compilers folks and with the formal methods folks, because my final wish is for compilers and automated front ends that are targeting all of the new backends that the area has been producing. So right now, the backend landscape, we've seen a little bit already, is kind of fragmented. And that's great because it's a result of the growth, but it's also bad because it means that it's very hard for any given backend to actually generate a computation that's really good for that backend, or generate a representation rather, that's good for that backend. So the result is everyone kind of tends to hand tune for their own backends, and so then there's little common ground where we can actually compare things. So instead, I think what we need to be doing is systematizing all of that implicit knowledge that everyone has about how to tune for their system, right? And all of this should be made automated. And I think that'll pay two dividends in two different ways. So first, that'll mean that people outside the area can reasonably start to use these systems, because the back end, once you give it a representation, for the most part, it just works. But getting to a representation from the computation that you want is a real struggle. And there are we've seen already there are a couple community projects trying to do this. There's SIRCOM and Bellman, and I helped to maintain an open source project that's derived from the Buffet compiler, and we get lots of messages on GitHub and like emails saying like, can you help me do this thing? So people really do want to do this, and I think the problem really is in just getting the front end to do what you want. So the other way I think this will pay dividends is inside the research area, because it'll mean that we can compare results in a more sensible way, and it'll let us kind of answer the real question that we should always be asking when we evaluate a practical system like this, which is, for the computation that I care about, what's the best performance that I can get, and which system should I use to get it? Because remember what I said at the very beginning, I don't know, a million slides ago, is that like the design space is huge, right? And this is good because it means that for any application that we care about, probably there is a point in the space where we can like have a very good answer for that application. And it's true that the absolute costs are pretty high right now, but I think as we've seen, there's like current and near future applications that work right now, and the costs are justified. And so we need to make that space bigger. And for that, we've all got still a lot of work to do, but maybe not till after lunch.
Any more questions?
So the thing that you did with the ASIC, with the prove and verify thing, so there's work actually going back to 88 with a proposal, and then there's work by, I think, Ron and Justin, where rather than having it as a single prover, have two provers, with some sort of separation between them, and I think it yields much more efficient results.
Absolutely, and I think we could even, maybe the implicit observation there is that model actually works pretty well in the hardware setting, because I can turn one of the chips off, right? So like maybe I really can get strong separation between the provers. So yeah, I think you're absolutely right. It would be one of the directions that would be very cool in the verifiable ASICs world, is to start looking at what else we can do with multiple provers, for example.
More questions? Guess it's lunchtime. Thanks, Riad.